All right, welcome everyone to the AI Solutions Free Flyer Wrangling Chaos Levering Tools for Cislunar Trajectory Design webinar today. We greatly appreciate you all taking time out of your day to join us from wherever you are on the planet. I'm Danny Brown, AI Solutions Space Products Account Executive, and one of your moderators for today. I'm joined by Chris Ulrich, also a Space Products Account Executive, and he'll be monitoring the Q&A for the webinar today. Next. Before we begin, let's go over some of the logistics for today. All attendees are muted and cameras will be off for the duration of the webinar. We'll be recording this webinar for future reference and playback on YouTube. We'll follow up with the slides after the webinar for everyone. You may also use the Q&A function to pose any questions during the webinar, and Chris will answer those at the end of the webinar. Additionally, you may use the chat function to network with other participants or AI Solutions staff on the call today. Next. Our presenter, Dr. Brian McCarthy, graduated from Virginia Tech in 2014, double majoring in aerospace and ocean engineering. After graduating from Virginia Tech, he worked for 2 years here at AI Solutions as a flight dynamics analyst in Greenbelt, Maryland. He started his graduate school at Purdue University in August of 2016 under Dr. Kathleen Howell, who may be in attendance today, so no pressure, Dr. McCarthy, and completed his PhD in May of 2022, where his research focused on computation and applications of quasi-periodic orbits in the cislunar regime. He currently works as a mission design engineer for AI Solutions at NASA's Johnson Space Center on the Gateway and Artemis mission design teams, where he is designing trajectories for the next era of sustained human presence in and around the moon. Welcome, Dr. McCarthy. Chris, and take it away.
All right, thank you, Danny. I appreciate it. First of all, I just want to thank Danny and Chris for dealing with all the logistics of this and getting it all set up, and thank everyone for being here. So I'll start off today, make sure I got my right screens up here. Start off today talking about, we all kind of have an idea that all sort of know that cislunar space is sort of one of the up and coming things. There's a lot of activity that's going on now, and it's being planned. The first of which is the Artemis program. So we know that Artemis 1 just launched recently, completed their mission successfully, and Artemis 2 is lined up to launch next year, along with Artemis 3, 4, 5, and 6 as well. There's a big push just around the Artemis program to send more infrastructure out to cislunar space, and one of the aspects of the Artemis program is also the Gateway, which is going to be a lunar outpost that's going to allow the astronauts to live in deep space for extended periods of time. Additionally, involving the commercial partners in landing on the moon is a commercial lunar payload services program, which is going to have commercial companies deliver landers and payloads to the lunar surface to understand the lunar surface science a little bit better. Additionally, outside of sort of the human spaceflight realm, we have the Oracle mission, which is involves the DoD and the United States Space Force. It's planning to send a mission to Earth Moon L1, as well as the Capstone mission, which has been flying successfully for almost a year now. It's a pathfinder for the Gateway in an L2 near rectilinear halo orbit. Now, with all this infrastructure going on, there's also a push to have better communications and position navigation and timing relays out at the moon. So the LCRS and the LunaNet programs are just one instance of a government, the government entity doing that, as well as there's other commercial companies that are planning to build their own lunar comm relay systems to support this growing infrastructure. Additionally, we have a number of international partners that have already launched missions or are planning to launch missions out to the lunar surface, or to the cislunar region, excuse me. So given all this activity, I've only mentioned a few here. There's many more that I didn't mention at all. We really need to have effective cislunar trajectory design and operations tools to facilitate all of this activity that's going to be going on out at the moon. So this is sort of my presentation today is going to sort of talk about some of the aspects of the trajectory design problem and sort of about the cislunar space in general and sort of how we define it and things like that. So an outline for the presentation today. First, we're going to talk about just what is cislunar space, and we'll talk then about the dynamics and sort of how that's different than sort of the near-Earth dynamics. Additionally, some trajectory design techniques, and then some final remarks and Q&A at the end. So cislunar in general, the name cislunar kind of alludes to the Earth-Moon neighborhood. So just to kind of define the word itself, and I'll talk about some stats here about sort of what this region encompasses. There's no rigorous definition right now of what cislunar is, but I'll just leave some stats here to kind of give an idea of the size of the region that we're talking about relatively. So the distance to the moon is right around 400,000 kilometers. It sort of varies depending on where in the lunar cycle you are. So this is about 100 times the distance between New York and Los Angeles. Additionally, this is about 300 to 400 times the distance from Earth to Leo, and about an order of magnitude greater of the distance from Earth to Geo. So this is a huge region we're talking about here, just distance-wise. Additionally, if we think about this in terms of volume, the volume of the region encompassed by the moon is approximately 10,000 times the volume of Geo. And so in this animation here is just a spacecraft that's spiraling out from the Earth out to Geo. And we'll see eventually it gets out to this green orbit, which is a Geo orbit. And then in white is the moon's orbit around the Earth. So you can see that if we think about this in terms of for defense aspects or surveillance aspects, this is a much larger region than everything that's encompassed inside of Geo. So for the defense aspect of things, it's a significant effort to now deal with this larger region that needs to be considered for space operations. So given those stats, we can take a look at a little bit about how some basic assumptions that change when you're dealing with a cislunar regime as opposed to, say, a near Earth or near a single body regime. So with the near Earth assumption, we assume that the Earth is really the main dominating body here, and that's the one that's going to basically tell you or give you the most information about what the path of the spacecraft is going to be. That holds true for both Leo and for Geo. But when we get out to the cislunar regime, it's different. We now have to consider both the Earth and the moon's gravity field simultaneously, and neither one of them can necessarily be neglected in most cases. Not only that, we also think about near Earth space in terms of a Earth-centered reference frame. And so we define that inertially, and all of our orbits are sort of based on that inertial reference frame relative to the Earth. However, in cislunar space, it's typically makes more sense to look at this in terms of a different frame. And that frame is going to be the Earth-Moon rotating frame. And so what that does, instead of considering both the motion of the moon and the spacecraft in, say, an Earth inertial frame, we lock the Earth and the moon in place, and we just have to worry about the motion of the spacecraft. So it makes it more convenient for determining motion or classifying motion by making this assumption. It's sort of a fundamental difference of how we consider near Earth space as opposed to cislunar space. Additionally, we have fairly significant, fairly sensitive dynamics in the cislunar regime as well. So if we just consider a mission that we want to send out to the moon directly from the Earth, and we want to use some of the cislunar dynamics in order to do that, we can see here on the left-hand side, the type of transfer we can do in order to do that is by leveraging the sun, Earth, and the moon dynamics all together. And with this sensitive interplay between all three of them, we can accomplish the objective of getting out to the moon. However, if we were to perturb our state at launch by just 1 meter per second in various directions, we can have two very different outcomes. We can have in the center here where we don't necessarily reach the moon and we miss it altogether, or we depart the Earth-Moon system. So this kind of highlights that the dynamics here are incredibly sensitive, that not only that's a challenge, but it also can be an advantage because we can move within the space for relatively low delta V costs. So additionally, there's different ways we can classify motion within cislunar space as well. So the traditional way of classifying motion in a two-body sense, so say for near Earth space, is the conic section. So we have circular orbits, we have elliptical orbits, and we have parabolic and hyperbolic trajectories. Now these generally are a good way to define all types of motion when you're in a region where one body dominates the gravity field. We also have convenient orbital elements to help us define these types of geometries as well. However, when we get into 3 and 4 body regimes, which encompasses cislunar space, we can classify the motion differently. And some of these structures may not necessarily be an accurate representation of what the motion is going to be. And the geometries look very different. So in this space, we can classify equilibrium points. So this is our, we call Lagrange points. And they're fixed points in the Earth-Moon system. We have periodic orbits, we have quasi-periodic orbits, and then we have chaotic motion. And so just looking at these on the right-hand side here, they're much different than our conic orbits on the left. And we don't necessarily have, again, as I mentioned, convenient orbital elements in certain regions of the space that can help us well define these. So it's a different design paradigm that we have to deal with. So some of the periodic orbits in the cislunar region, I'll talk a little bit about. And the one thing I'll point out here is that they all have very different geometries and they all look very different. So they have advantages for different mission profiles if you have different objectives and we want to reach different regions of cislunar space. So the L1 and L2 Lyapunov families exist in the Earth-Moon plane. They're seen here plotted in the Earth-Moon rotating frame, looking down the XY plane. Additionally, we have the distant retrograde orbit family, which also exists in the Earth-Moon plane. And one of these orbits from this family was used as a destination for the Artemis 1 mission. And so that's one of those orbits. It would be kind of in the green region here. Additionally, we have probably some of the more well-known orbits, the L1 and L2 halo orbits, and those are shown here, the northern and southern L1 and L2 halo orbit families, and these exist out of plane in the Earth-Moon system. Additionally, we have the L2 northern and southern butterfly families and the L1 and L2 vertical orbit families. So again, this goes back to all of these orbits have very different geometries, so they can give us advantages for accessing different regions of space that we would otherwise not be able to if we made the underlying assumption that we can only use conic motion. Additionally, to take it one step further, we have quasi-periodic orbits, which are a little more exotic than periodic orbits. And sort of this animation showing here is that they don't necessarily exist as a closed curve, but rather they exist on a surface. So as each one of these are playing out, we can see that the trajectory traces out on the gray surface for each one of these animations. And so if we run these for an infinite amount of time, they will eventually cover the entire gray surface. And so what we can do is in the next animation, we can represent these quasi-periodic orbits as gray surfaces. And so just like how we had families of periodic orbits, we also have families of quasi-periodic orbits as well. So in these animations, at each snapshot in time is just showing a different member of the quasi-periodic orbit family. And so again, this goes back to not only we have families of periodic orbits, we have families of quasi-periodic orbits. So there's a lot of different types of motion we can leverage in this space for different types of missions. So in addition to periodic orbits, quasi-periodic orbits, and equilibrium points, we also have stable and unstable manifolds associated with different different types of periodic and quasi-periodic orbits. And so what these do is they allow us to have maneuver-free paths into and out of our different types of orbits. And so this is really nice because it helps us move between the space for a relatively low delta V. So as I mentioned earlier in the presentation, the dynamics are really sensitive. That presents a challenge. However, it's also something that we can leverage to move between the space. And so what this animation is showing on the left-hand side here is just a set of manifold trajectories that are departing an L2 quasi-halo orbit. And so they slowly sort of wind off of this quasi-halo orbit in gray and move around the cislunar space. So given these types of orbit classifications, there are different models we can use to to model the motion in cislunar space and model the dynamics. We have 3-body models and 4-body models, and by no means this is the all-encompassing list. These are just sort of some of the popular models that are used. In particular, the circular restricted 3-body problem is most likely on the top of the list, where we consider the motion of the Earth, the Moon, and the spacecraft. We make the assumption that the Earth and the Moon are point masses, and they orbit about their common barycenter, and then the spacecraft moves in that space as well as a massless body. Additionally, we have the Hill restricted 3-body problem and the elliptic restricted 3-body problem, and then 4-body models, which include the Earth, Moon, and the Sun and the spacecraft, are also relevant for this problem because sometimes we want to include the Sun in our preliminary design process, and because different motion exists when we include the Sun even further. So some tools for trajectory design that I like to use or typically like to use. Again, this is sort of not an all-encompassing list, but just 2 that I found very effective for different types of analyses that I've done. So first would be different shooting or collocation methods. You can even lump optimization methods in here. Additionally, we have Poincare maps, which are a way to take a higher dimensional data set and reduce the dimensionality so we can actually look at it and look at sort of how some of the motion is organized in a dynamical system just in general. And so we apply this to the astrodynamics problem since the 3-body problem and the 4-body problem are dynamical systems. So first, I'll talk about our shooting and collocation methods and sort of what they are and why they're useful. So we'll consider a multiple shooting targeting method just for representation's sake. So let's say we have a scenario where we want to go from the Earth to the Moon. So point A is near the Earth and point B is near the Moon. Now, it'd be really nice if we could just find a trajectory that would get us there. We get the initial conditions and they satisfy all the constraints we want. But this is pretty much never the case. And so we need to find other ways to accomplish this objective. And one way we can do that is by setting this up and having different sets of arcs that we find through different types of processes. So you find arc 1, arc 2, and arc 3, and then ultimately you run a shooting process and try to connect them together. Additionally, we can implement other constraints in here. So let's say, for example, we want to get to some altitude or some apse at the Moon. We can also include that as well in one of these type of shooting problems. And so ultimately, what we would want to do is, with the successful shooting problem, we would connect all the segments together and satisfy the constraints that we set for the problem. Additionally, one thing that's important too is we want ideally we want the initial guess that we have to match closely to what our final continuous solution is. And so that's a really important part. Again, given the dynamics are sensitive in this region, we want to ensure that when we're scaling up our fidelity, that we maintain the geometries that we want. Now, just a few other methods to accomplish this type of targeting method. We have 2-level targeting, which breaks up the position and velocity components of this corrections process where you're kind of stitching different segments together. We also have collocation, which turns this into a implicit run kutta method and then solves for the same problem. And also we have optimization, and there's a wide array of different types of optimization methods out there that are gradient based or non-gradient based, depending on the application, that are useful to solve this problem. And so, we'll talk about the application of some of these targeting methods a little bit later. But the next tool I want to talk about too is Poincare maps. So, what is a Poincare map? And so, the way I like to look at this is very visual because it's a very visual tool. So, if we define some plane or some hyperplane here, where this can be a physical plane in space, this can be a mathematical definition, and we take an initial state that exists on this plane. We can take that initial state and propagate it forward in time. And sometimes it will return to the same plane, or sometimes it will not. Sometimes it will satisfy the condition, sometimes it won't. However, when the times it does, we can record that and use that information to understand some of the motion in the region. So for example, if we pick a state such that it returns to the exact same location on that plane every time, we know that we have a periodic orbit, because this motion is just going to go around and around and around again, and it's always going to return to the same spot on this hyperplane. So, that's just one example, but it can be useful to pull out some of the motions for the sea of chaotic data that we may have. So some examples of how we can define this hyperplane sigma are a periapsis, which is a close approach to a body, an apoapsis, and a physical plane, say the XZ plane, for example. So we'll talk about the example of a periapsis. So what is a periapsis? As I mentioned, it's going to be a close approach to any particular body. So in this representative case here, we have the moon, and we have a close approach to the moon. Now, what the condition is of when we achieve a close approach to the moon is when the position vector and the velocity vector are perpendicular. And we can define that with a math equation over here on the left-hand side. So these two conditions satisfy the fact that we're at a periapsis condition. So if we take a trajectory and propagate it forward in time and look at all the times that it satisfies this periapsis condition, we can record that and see what happens. So we take just this green trajectory here on the left-hand side, and all of the white points along this trajectory are considered periapsis points. And so if we take that, we remove the time history of the trajectory and just leave the periapsis points, we'll notice that we have some interesting features over here on the right-hand side, that it's symmetric across the y-axis, and that they're all grouped together. And so it's an interesting feature just for this one trajectory. However, we can do this for a whole bunch of trajectories and then look at what it leaves us. So if we propagate a whole bunch of trajectories forward in time, and then we record all the periapses of all of those trajectories, we can create a periapsis Poincare map, and that's shown here in the center. And just without even really knowing anything about trajectory design or Poincare maps, we can see that there's some interesting features about this map. First of all, over here on the right-hand side is probably the most striking one. We have these concentric ovals here, and so it's just, again, that's sort of an interesting feature about this. As well, we have, on the bottom side and the top side of the moon here, we have these, again, sort of concentric structures, and then sort of these very interesting features over here on the left-hand side. So if we take a look at the trajectories that are associated with some of these points, we can see that they have motion that is also interesting as well. So just inside of this concentric region over here on the right-hand side of the map, we can see that we have a very bounded orbit around the moon. And that's because all of the points are all the periapsis points are very close together. So the trajectory is returning very near to the same location every time it goes around. Additionally, in the middle here, this green trajectory exists in this concentric set of concentric points on the bottom side of the map. And we recover this as the same trajectory we looked at before. Additionally, if we look at points sort of in this sea of what looks like, not a lot of organization, we can see that we have a trajectory that's a lot less bounded. It has periapsis points that spread out a lot more, and they're not necessarily as consistently in the same location every time. So again, this is sort of an interesting tool that's really useful depending on what type of analysis you're doing. And so one type of tool we were developing here at AI Solutions that's really useful is the Deep Space Trajectory Explorer, and the whole sort of fundamental aspect of the tool is built around these maps and using them for design. The tool focuses mostly in lower fidelity models, so the circular restricted 3-body problem and also the 4-body problem. And some previous studies that we've used this tool for are identifying different types of orbits for ocean worlds, so for the outer planets, Saturn, Titan, and Enceladus. Saturn, Titan, Saturn, Enceladus, and then also Jupiter, Europa. Additionally, we've looked at using this tool for impact and recontact analysis for the Lunar Gateway, just higher dimensional data visualization in general, because this is as we're applying this to the astrodynamics problems, it's sort of a subset of a just data visualization problem. Additionally, we've used this tool to generate ballistic lunar transfers to libration points in cislunar space, and I'll talk about an application of that a little bit later. And then most recently, I've used this for coming up with initial guesses for an Artemis-like mission out to an NRHO. So in some of the tools for trajectory design that I talked about, there's really different strategies, different points here that I want to make that are sort of critical to design in this regime. Now, these are by no means the only ones, but these are sort of the 3 that I found that are really important in this regime to perform a trajectory design process effectively. So first is coming up with an initial guess strategy. So this means when we're using these targeters or these optimizers, they all require initial guess, and rarely do they ever have a self-starting method in order to generate a trajectory, just especially given the sensitive dynamics. So having a really robust initial guess strategy is going to be important. Second is how we can take solutions from a lower fidelity model and move them into a higher fidelity. So with most engineering design processes, we like to move in fidelity from lower to higher just because if you're starting in the higher, that's going to be a lot more difficult. There's a lot more knobs to turn. So sort of moving up in fidelity is a good engineering practice. Additionally, it's important to identify families of solutions and not necessarily point solutions. And so what I mean by this is you want to avoid having to go back and redesign your entire trajectory when inevitably your mission constraints are going to change along the way that are, controlled by forces that are outside of the mission design team. So it's important to have a good process in place to identify families so that when mission constraints change, you can respond to those very quickly and very effectively. So first, we'll talk about the initial guess process and generating those. So as I mentioned, it's really important that we have a good initial guess for all types of differential corrections, optimization, and collocation methods in order to ensure that what we initially find in the preliminary design process actually carries over to the higher fidelity problem. Additionally, having a good initial guess of the problem I talked about earlier, where we have different arcs we're stitching together. We ideally want to sort of maintain the geometry when we're stitching the problem together in general. So a good initial guess, we ideally will yield quick convergence and maintain our desired characteristics. And so when we have a bad initial guess, this can cause unpredictable behavior in the process of either changing the fidelity or stitching different arcs together, or it can cause non-convergence at all, and that's obviously something we want to avoid. So I'll walk through a scenario of how we can use the DSTE in order to do that. So first, let's consider a scenario where we have we want to go to some L2 halo orbit, and we pick one. This is just showing them in the Earth-Moon rotating frame. We pick one that we want, and this satisfies some sort of set of mission constraints that we have been levied. Now we can use a tool in the DST to help work this problem in reverse. And so what we're doing here is we're taking this orbit that we have found in, that we've decided on this is going to be operational orbit. But we can work the problem backwards and use Poincare maps in order to help us find trajectories that get out to this orbit. So we'll take a set of trajectories, we'll propagate them in reverse time, and then find out when they get close to the Earth. And then when we run those in forward time, they will be trajectories that get us out to our destination orbit. So just in the tool, we have a number of different types of filtering parameters and things like that that can help us effectively isolate the trajectories that we want. So we want to avoid ones that escape. We want to keep them bounded with a periapsis radius close to the Earth. And then we want to remove ones that have a sort of a retrograde motion at the Earth, so more representative of a launch condition. And so what this does is it gives us a bunch of periapsis points. So this is a periapsis map here. We can see that we have a number of points on the animation here that show, okay, some of our trajectories satisfy the criteria that we set by not escaping and staying within some bounded periapsis radius of the Earth. And so one thing I'll stress too about this tool is that it focuses on the sort of the lower to medium fidelity analysis first. So again, we're focusing first on the lower to medium fidelity analysis, and then you ultimately want to scale up to higher fidelity instead of starting in high fidelity right away. And so if we take a look at some of these trajectories that we've just generated, we have a whole bunch of them that satisfy our constraints. So we can just pick one and then render it in the Earth-Moon rotating frame here. And we can see that it satisfies that we get all the way from the Earth all the way out to our L2 halo orbit. And additionally, as I mentioned, this can serve as an initial guess, which we would pass to free flyer, since free flyer is better at sort of the higher fidelity modeling of all the space environment. So we'll talk about that a little bit next here. So given that we found initial guess, or if we have some way of getting initial guess, we can take that and transition it from low fidelity to high fidelity. And so what that means is that in these lower fidelity models, we make assumptions about the locations of the Earth and the Moon and how they orbit and how the spacecraft moves in that vicinity. But when we're moving to operations, when we actually want to fly a mission, we really need to have a high fidelity model that can represent our reference trajectory in higher fidelity. So ideally, we want one of these transition methods to be flexible for different mission constraints and also maintain our characteristics of our initial solutions that we find. So again, mission constraints can change along the way, so we want to be able to respond to that quickly when that ultimately comes. So we want to, ultimately avoid unpredictable or unpredictable behavior, or losing the geometry that we were looking at for our initial solutions. So if we take an example of a trajectory that we would get out from an initial guess here, shown in the upper left. So this is, again, a transfer that goes from the Earth all the way out to a near rectilinear halo orbit out at the moon. We can see that in this image, there's a few discontinuities here. And what this is indicating to us is that this trajectory is not continuous. So when we move the initial guess into a higher fidelity model, it doesn't connect completely. And that's kind of what we would expect, because the dynamics are going to be different. However, when we use a targeting process in order to satisfy continuity between all of these different white nodes on here along the trajectory arcs, we ultimately can move it into the higher fidelity and maintain some of the trajectory characteristics that we originally wanted from our initial guess. So this is sort of a demonstration of how we can successfully take an initial guess from lower fidelity and move it into higher fidelity. In addition to the transfer problem, we can also do this for operational orbits. So for some of these libration point orbits, they're really sensitive. So just placing a spacecraft on it and just letting it go, it's not necessarily going to stay there for all time. So having a reference trajectory or a baseline trajectory in order to do station keeping, or even just do analysis on to figure out, if you have eclipsing or comm issues, you want to be able to do that. So over here on the right-hand side is just showing if we take an initial guess and we feed it to a targeting process, we can maintain the characteristics of the orbit and generate a long-term reference. So I think this is 10 revolutions of an L2 halo orbit that we can correct to make fully continuous for all 10 revolutions of that. So with that, the last sort of point of the three that I was talking about is having families of solutions. So having a point solution, what I mean by a point solution is just one isolated reference or trajectory that you do all your analysis with. It can be limiting in terms of flexibility for changes in mission constraints. And what families of solutions do provide greater flexibility and allow you to respond to changes in the mission design process or trajectory design process throughout the whole development of the mission. And so one thing I'll point out too is that the generation of these families of solutions can happen both in the lower to medium fidelity and also in the higher fidelity. The lower fidelity gives you a good understanding of what sort of the flow is, the dynamics are in a particular region of space, and having families of solutions in high fidelity can have sort of this bank or this this set of trajectories that can help you respond to changes in mission constraints, as I mentioned earlier. So for an example of families of solutions in our lower fidelity model, so this is all in the circular restricted three-body problem. We can take a quasi-periodic orbit over here on the left-hand side in gray, and if we want to move from, this is an L2 quasi-halo orbit, we can move from the L2 side to the L1 side using a what's called a heteroclinic connection, which is a maneuver-free connection from the L2 side to the L1 side. And we'll notice here is as this animation plays out, it's just rendering different trajectories in white along the animation. And so what this is telling us is that this is a family of solutions from this gray orbit to a different set of blue orbits on the left-hand side here. You can see sort of the blue surface is shrinking as this animation plays out. And so what this does is it shows us that there is the flow follows a certain path here to get from the L2 side to the L1 side. And that's interesting, and it's useful for understanding, okay, if things change down the line, I kind of have a good understanding there's going to be other solutions in the vicinity that can provide the same sort of path to get from the L2 side to the L1 side. Now, this type of transfer going from the L2 to the L1 side is something similar to what the Artemis-Themis mission did a little while back. Now, additionally, we can take one of these white trajectories and feed it into a targeting process to change from low fidelity to high fidelity, and that produces what we see on the right-hand side, which is in the Earth, Moon, Sun ephemeris model. So as I mentioned, also we can also not only do this in the lower fidelity, we can do this in higher fidelity as well. So if we're looking at a problem where we want to go from the Earth all the way out to the Moon, we can generate a family of solutions that does that. And so for this particular problem, we're looking at going from Earth directly out to the Moon into a polar 100-kilometer altitude lunar orbit. And so each one of these trajectories is shown in the Earth and Moon, but I'm sorry, the Earth-centered inertial frame, and they're colored by the insertion delta V. So again, if we have sort of changes in our launch geometry, if we know we're going to be launching at a higher or lower inclination, having this set of trajectories can be useful to be able to respond to those changes quickly. And then again, on the right-hand side here, we can render this all in the Earth-Moon rotating frame, and you can see they sort of wind around the Earth-Moon system and ultimately satisfy the constraints down when we get close to the Moon. So these, all these renderings are done in, in FreeFlyer in the high fidelity model here, and they're useful, as I mentioned, because we have, we want to be able to have all these different types of options and be able to use them readily available. So setting up your trajectory design process in order to be able to have these types of trajectories built or a way to build them quickly is going to be really, really useful. So given all that, apologize if I talked really fast. Just some final remarks here. So as I mentioned in the beginning, this paradigm that we have for cislunar space is much different. Our dynamics are different. They're a lot more sensitive compared to near Earth space. So we're going to have chaotic motion that is going to be can be challenging to deal with, but it also can present opportunities to help us move within the space for low delta V. And so, given these sensitive dynamics or this unique sort of system we're working in that's different from near Earth space, we need the proper tooling in order to effectively leverage the dynamics to our advantage and look at a wide variety of these different types of trajectory options to ensure mission flexibility. And so here at AI Solutions, we're keeping all of this in mind and developing some new flight dynamics tools and capabilities that can help leverage these types of tools for the trajectory design process. And so with that, I appreciate everybody's time for being here, and I'm happy to take some questions and answers.
Brian, thank you. I just want to thank you again for taking the time to educate us on cislunar space and orbits. We all know space is hard, but I think you make it look easy, particularly with these visuals, which is a great addition, to some presentations that I'm sure folks have sat on in the past. So thank you for those. Now, we are going to dive into some Q&A. So if you do have questions, feel free. Now is the time to drop them into the Q&A chat. I do want to start with my own question. However, Brian, just for my own edification, I think if we jump back to slide, I want to say 39, you were talking about the families of solutions.
Sure.
Would you be able to give a little more information about why point solutions have limited usefulness?
Yeah, sure. So we ultimately need a point solution for a mission that we're going to fly. But during the design process, we know that things are going to change, and that one trajectory that we find right at the beginning is not going to is most likely not going to stick as the one we're finally going to fly. So having families of solutions or avoiding just building your entire trajectory design process as just a way to find one point solution is not going to be a good use of time for development. Spending the extra time to have a trajectory design process that can develop families of solutions, or not necessarily just single point solutions, is going to help you in the long run to help that sort of go back and forth as things change. You can feed more answers to the stakeholders and things like that. So that's sort of the gist, is really setting up the design process to avoid having to go back, roll all the way back to the beginning and start design completely from zero all the way over again, and then going through turning the whole crank again to find your one point solution. That's just not necessarily an effective use of time, in my opinion.
No, thank you. Thank you. Now, when you were going through this presentation, and correct me if I'm wrong here, these were essentially high thrust applications. Is that an accurate statement?
That's correct. Yep.
Could you talk a little bit more about low thrust and kind of how that plays into these solutions that you highlighted?
Yeah, absolutely. So the tools that I've shown off here are, yeah, as you mentioned, they're sort of they all look at ballistic arcs and sort of high thrust, impulsive thrust type designs. However, these tools are still applicable to a low thrust problem. It's just really, setting up the flexibility to if your mission needs a low thrust and having that in there to satisfy, that requirement. So I wouldn't necessarily say that they're sort of specific to high thrust. They're useful for low thrust as well. This sort of gives a general overview of the types of tools and the way you want to set up your design, workflow so that you can be agnostic to high thrust or low thrust for that matter.
Sure, sure. Are there any specific nuances that define one versus the other?
Yeah, sure. So with low thrust, you're going to have these longer trajectories or these longer thrusting segments that can't necessarily be assumed to be just at an instant you're changing your velocity direction or magnitude. So you can set up your preliminary model, for example, to include structures that have low thrust. And then feed those, however you construct your initial guesses or your initial guess arcs using those low thrust structures. But it's really the difference between the assumption that you make for high thrust, as you can assume it's an instantaneous change in velocity, whereas with low thrust you're going to have you need to think about, okay, this thrusting arc is going to be thrusting for hours or days, for example. And you need to build that into the initial design process as opposed to waiting to the end, designing a purely ballistic or impulsive type of solution, and then trying to force it to be low thrust. If you think about it towards the beginning and you build that into your process in the beginning, it's going to be a lot easier to sort of be agnostic to how thrusting works for your vehicle.
Okay, no, that's super helpful. Again, folks, if there's any other questions, feel free to drop them in the chat. Brian, if you, and I'm sorry to keep making you jump around here, buddy, but if you go back to slide, I want to say 29, where you had the point care map. Would you? Yeah, see, I think it's slide 29.
Right here?
And it's not really an in-depth question. It's more of just some curiosity around the time it takes to generate this type of visual. Do you have any insight into roughly how many trajectories you're propagating and for how many revs?
Yeah, that's a great question. So this map, for example, I think is a couple thousand trajectories, and there is, I think, a couple 100,000 points on here, most likely. And the way that this tool is set up is it's because you're dealing with a sort of a low to medium fidelity model, the numerical integration that's required to evaluate all these trajectories is a little bit faster than if you were to do, a high fidelity where you're using, the ephemerides of the planets. It can numerically integrate them faster, but also it does multi-threading. So when you feed it a job, it basically just spreads it out over all your cores, integrates them all forward in time, and then it can, if there's certain constraints you have on generating this map, it will remove those trajectories that don't satisfy those constraints on the fly. So it's not generating all the data, sifting it out at the end, and then rendering it. It's sort of rendering as you go and filtering out as you go using multi-threading. So I think that answered your question. It took maybe a minute or two to generate this map.
No, awesome. Thank you. I know we sometimes get those types of questions about the program, so I did want to highlight that. We do have a bunch of questions now coming in to the chat and the Q&A. I'm going to go to the Q&A first.
Okay.
So we have a question here. How does Dr. McCarthy converge his ephemeris solutions? Do you do a direct transition and converge there, or do you slowly transition from the lower fidelity models?
Good question. So I personally, for these examples, just went straight from, I think my examples were either in the 4-body or the 3-body problem, just converted them directly to the high fidelity model. However, there's ways of doing sort of an intermediate fidelity where you can set up to scale between the lower fidelity model and the higher fidelity, and sort of run a process to do that as well. If there's really some characteristics that are really sensitive and that you need to maintain in the process of moving from lower fidelity, higher fidelity. But in my case, I just went and transitioned them directly using a multiple shooting scheme. Thanks for the question.
A couple more from the chat here. Are there any standard references for deep space or cislunar trajectory design and optimization techniques that are widely used?
I wouldn't say there's one sort of manuscript or one end-all be-all reference that sort of encompasses everything. I think because this is sort of a new, not necessarily a newer regime people are designing in, but because there's the industry is really burgeoning and sending a lot more infrastructure out there. There's still the jury's still out in terms of what's the one, if there ever will be, what's the one sort of finite reference to look at to be able to do all these types of things. There's a bunch of different references out there. There was from academia and also from industry that have worked on these types of problems before that are particularly useful. I'm going to give a shout out to my previous research group. We did a lot of work in this sort of cislunar regime under Dr. Howell. So some references there are really good. It really sort of depends on what you're looking for.
Awesome. Couple other questions. Does DSTE make use of GPU calculations?
It does not currently, but we have used it on the Oracle Cloud before, so we've been able to farm these jobs out to Oracle Cloud, and it evaluates numerically, integrates the trajectories, and then feeds the data back. But specifically GPU hardware, we have not set it up on there, but it's all written in Java, so it is it's set up to sort of be agnostic to the hardware you're running with, and it you know, if you have a GPU you can work with, like, it should be able to run it. I just never have tried it before because I don't have a GPU to work with.
Awesome, absolutely. All right, looks like we have another question here. Let's see. So how does DST interact with common trajectory design tools? Let's say GMAP, for instance, or SDK?
Great question. So obviously, since we're AI solutions, we have integrated a little bit with FreeFlyer, but it all the tool has its I guess it has several different types of file formats it puts out. So it just has, you know, ASCII files that have the data in it that can be read into any other tool. We're slowly migrating over to using a JSON style format, just because that's a little bit more, I guess, instead of having a custom format that everybody has to, you know, build a ingest, you know, format or two, you know, JSON is a little more standard. So that's sort of what we're working with, and sort of in terms of interfacing with other tools. It'd be great to have, you know, to have it's sort of agnostic to any tool, but we're still working on that.
Awesome. No, thank you for that. All right, we've got about 10 minutes left here. I'm just going to do a quick check to see if there's any other questions that have come into the chat. It looks like we have a new one here. So to start the design process for trajectory design, does the choice in the initial low fidelity model change depending on what type of orbit family the final insertion will be in? And there's a second part to this question. And how do you verify that the coverage solution represents the true geometry of the orbit?
Sure. So I think in essence, to answer the first question, yes, really your low fidelity solution ideally should dictate what your high fidelity solution is going to be. It's never going to match exactly, just because the dynamics are just inherently different. The process, it kind of goes back to like the process of having a really good method to find initial guesses or generate initial guesses is critical to this problem, because it's the anchor to all the other ones in the design process. So having tools to be able to build initial guesses or search the initial guess space effectively is really, really important, because you can have a situation of the insertion constraint changes, and so you need to come up with something different. So having that sort of initial guess process really ironed out can help you respond to that quickly. Yeah, I think that sort of gets it. Hopefully that sort of gets at the question. And then to the second question, how verifying the converged solutions. I think you ultimately want to have a good idea of what your constraints are at the beginning and then also at the end. And if you can levy those constraints throughout the process, or sort of slowly phase them in throughout the process, I think that will should satisfy the if you want your true converged geometry of the orbit. I guess in the case of, let me show an example here real quick. In the case of having a particular trajectory exactly how you want it, you're going to want to set up your problem in a certain way to enforce that. So let me go to a second here. So for this example right here, so on the top we have our initial guess, and we have a NRHO that looks like this, that goes around the moon. But when we move it into the high fidelity, it kind of moves around. The apoloon locations are a little bit different than in the initial guess, so that sort of changes. However, within the convergence process, what you could do is you could set it up so that you converge the orbit first, so this NRHO first, and you say, okay, this is my reference, I want to be on this one. And then you can build solutions around that and say, okay, all of my transfers out there need to get to this reference orbit. So don't include that in the corrections process every time. You're just correcting the trajectory to get you out there, and sort of looking at different solutions along this reference that you build ahead of time. So it's kind of being able to have these different pieces or these different blocks that you can mix and match out. Does that kind of answer the question, hopefully? Good one.
No, absolutely. We do have a few minutes left. If you're willing to take a couple more questions that are coming into the chat.
Absolutely.
Let's see. Let's start here. One from Jonathan. Are the Poincare maps the closest thing we have to trying to build our mental model and intuition for multi-body orbits? Much like we use orbital elements to visually describe two-body orbits, are these maps the future for the multi-body orbits?
I think great question. I think they're a really useful tool, and they really help us understand the space, and they can give us a lot of insight that we would otherwise not have. I think the challenge with them is that what are the conditions you're trying to set up to solve to build your map is a big sort of area. That's an area of research, is how do you define the map. So I showed periapsis maps, but there's other ways to define it. And then how do you represent, if you're just doing points, that gives you 2 dimensions of data. But if you want to do 3 dimensions or 4 dimensions, how do you represent that on a map? You can use vectors additionally. You can use vectors on there. You can use you can plot it in 3D to include that extra dimension there. But it's a useful tool. I don't know if it's the end all be all, but it's very useful in this design process. One thing I will say too is that you can also use these maps and sort of stack them one on top of each other to find out, okay, if you're at one map on one energy level and you have a point, and then you have another map that you're trying to match the energy level, you can sort of do this process of finding changes between the maps or moving between the maps in that way to sort of look at more dimensions or more energies as well. So yeah, I hope that answers the question. Thanks, John.
Brian, we're going to take one more question here because we are starting to run low on time.
Sure.
The question is, will Free Flyer users have access to DSTE? And I think that answer is, and Brian here kind of keep me honest here. We know that those two software offerings are separate products, so you will not necessarily have access to DSTE through Free Flyer. But if you are interested in leveraging that software and that functionality, we can definitely work with folks to explain how those packages work and what we can do to take advantage of those features.
Yeah, and the thing I'll say too is that I for a lot of this analysis, I use DSTE and Free Flyer very closely together, and the integration between the two is useful. Both Free Flyer and other tools as well. But we've tried to set it up so that knowing if you're going to get something or you want something out of DSTE, it can be easily used in some other tool, and the way we produce the results of DSTE are useful to another tool that you would perform some of their analysis in. So we're thinking about that along the way too, in terms of both being able to access it and also the interplay between both tools.
Thank you, Brian. If you wouldn't mind jumping to the second to last slide, but before folks hop off here, we will follow up with some of your questions that we didn't get to today via email. However, I just want everyone to take out your phones for a minute, open up your camera or your QR code reader, take the next 90 seconds or so to register for our webinar in Q4. In October, we're going to have our very own Nate McCown, our Free Flyer support engineer, will be taking folks through the world of optimizing your constellations using Free Flyer in an effort to show off the capabilities and also tips for getting the most out of your mission planning. So don't forget to sign up for that. That's going to be in October the 25th, around the same time from 1 to 2 p.m. So we're definitely looking forward to that. And I'll leave this slide up for a minute, but again, I just want to thank everyone for attending today. Brian, especially you, for taking folks through all of these great visuals and details about Cislunar space. We had over 100 registrations. I think 100 folks even joined this call today. We hope you got some value out of this conversation. If we didn't get to your question today, or if you want to learn more about Free Flyer, maybe join one of our virtual demos or learn about the entire suite of space engineering software, definitely don't hesitate to reach out to us at sales@aisolutions.com. You can visit our website, freeflyer.com. You can also feel free to engage with us on social media. We will be posting a copy of this recording on YouTube in the coming week. We're also going to share out these presentation slides. And again, if you continue to drop questions into the chat, we will be sure to follow up with those as well, because we do have folks' contact information. So thank you again, Brian, Danny, for helping organize this, and all of the folks here in attendance for making this presentation what it is today. Give one more round of applause to Brian and thank you all.
Yes, thanks everyone for coming. I really appreciate it.
All right, if you just jump to that last slide, we'll end it on this, folks. Thank you so much. Enjoy the rest of your week. And again, please feel free to reach out if you have any questions or would like to learn more about Free Flyer or DST capabilities and functionality for your mission operations.